Okay, so rational functions and in behavior is what we're going over. As you can see, in our objectives, we're gonna have to recall some stuff. Long division, synthetic division. These are things that we did in Algebra 2. Factoring polynomials. And then we're gonna talk about determining the quotient of two polynomials. So dividing. And then describing our in behaviors from there, okay? Here we go. Essentially, a rational function means that you have a polynomial in the denominator, okay? And in the numerator. So when you have a rational function, it's written as, that's not what it's written as. Let's try that again. We're going to call it R of X. Let's try again. Oh, there we go. R of X equals N of X divided by D of X. So we have a polynomial in the numerator, but the main thing here is that we have a polynomial in the denominator. And that's what makes it a rational function. Okay, things start getting a little funky for us. All right. What do we remember about being in the denominator? What can you not do in the denominator? That's square root. Say it loud, confident. There we go. We know that our denominator cannot equal 0, right? The denominator cannot equal 0. Just reminding you. All right. So we're going to start off slow with things that we should hopefully remember. All right. When you're analyzing a rational function, I don't know why mine is so tiny. Hopefully yours isn't. When you're analyzing a rational function, the first thing you want to do is make sure it's in factored form. So our number one thing we want to do is factor. Okay. What kind of factoring can I do with this one? How can I factor my denominator? By 2. What do I ask myself? There's no GCF. Good. We do always start GCF. That's step 1. After that. What? There we go. We're asking ourselves what multiplies to give us 12, but adds to give us. Yeah, remember that? Mental factoring. Yeah. Oh, that's what you. Yes. If that's how you think of it, Hudson, you're correct. Reverse FOIL. Okay. So we have X plus 3. What multiplies to give me 12, but adds to give me -8. 6 plus 2. What kind of 6? No, say that again. Say it, not 6 plus 2. What do they have to be? They both have to be -6 plus -. There we go. So our factors would be what? So we have X minus 6. You see nothing. You saw nothing. No, it's a parenthesis. It just got weird. Yeah. I made it better. See it now? Are we friends? Okay. And so we've now factored. Done. After we factored, we then are going to ask ourselves, can I eliminate anything? Yes. Is there anything that can be eliminated? Step 2, eliminate. Can I eliminate anything? Womp, womp, womp. That's like my favorite part. Is to just go pew, 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 but I can't do that. So there is no common factor in the numerator and in the denominator. So we keep going. Step 3 is we're going to set our denominator not equal to 0 to figure out what our values are. That's how I remember it. I have to write it that way in my brain. So taking my factors in my denominator and setting them not equal to 0. So we have X minus 6 not equal to 0. And we have X minus 2 not equal to 0. So what would X be? X can't be what? 6. And X can't be what on this one? 2. What's 6 minus 6? That's a... Oh my goodness. Okay. So these are my restrictions. Agree? Anyone's like, I have no clue. And you're absolutely correct. So therefore, when I write it as a domain, my domain, we're going to write it in interval notation. Starting from left to right. Where do we start on the left? All the way to the left is negative infinity, and I'm traveling along. Which one of my boundaries am I going to hit? 2. She said 2. We just didn't hear her, but she said 2. And then we're going to pause, and we're going to keep traveling. I know you know how to do this. And then we keep going to infinity. It's building on that. And reviewing from last year. All right. I didn't say it was hard. Those words haven't even came out of my mouth.
You're just trying to find reasons why it's not.
Yeah. Okay. I said we're going to review from Algebra 2. Literally said that in the beginning, but it's cool. All right. Does it feel like a little bit of review now? A little bit somewhere in your brain? This is new information? Okay. That's cool. That's cool. All right. We can lie. There's videos of me teaching this, so I know it's true. All right. What are these called? Those areas where I cannot equal. What does that mean I have? I know you know it. What are the areas where I cannot equal 0 called? What kind of asymptotes? Vertical. And the reason why we have these boundaries is we have vertical. I don't know why I was hesitating on spelling asymptotes, but I'm pretty sure that's right. I tell you all the time, x equals 2 and x equals 6. That's where our discontinuity happens. Because when you did your parent function review, rational functions have asymptotes, right? Remember that from your little beautiful presentations? All right. So that's our Algebra 2. That's our Algebra 2 review. Yes? So we're going to build on this knowledge that's already in our brain. Got it? All right. We're going to build on it because we're in pre-cal now. We're no longer just going to keep doing Algebra 2. All right. So what turns this into pre-cal is when we're starting to describe our end behavior. Okay? And making sure that we can read our arrow note. Just keep doing whatever you're doing. Our arrow notations. Okay? So when we're reading, because there are asymptotes, that means that we're no longer always heading towards infinity anymore. Does that make sense? We're now also heading and going away to our asymptotes. Does that make sense? Okay, so we're not always heading towards infinity anymore. We can also be heading towards an asymptote. So when you're writing, x is going towards your asymptote. That means the negative means I'm approaching from the left as x goes to your asymptote from the right. Makes sense because that's plus means I'm going from the right. Okay, we already know that this means x is going forever to the right. This means x is going forever to the left. But because of theirs being asymptotes, we also have f of x is going towards the asymptote. So our values are approaching the asymptotes, but will they ever touch it? No, not necessarily. Or our values are going forever to positive infinity or forever to negative infinity. The new piece here is that we have to acknowledge that there are asymptotes, okay? That's the new part when we're writing our limit notations. Got it? Other than that, did we already do the other forms of limit notations? Yes, we did, Bob. We did. All right. So when we're talking about vertical asymptotes, we're going to let that be x equals a. So your vertical asymptote is going to always be x equals a. And it's going to be x equal because y'all remember oivux? Oivux. Horizontal means that it's going to be 0 slope and y equals. And vux means that it is vertical and x equals oivux. Okay. All right. So if I'm talking about a vertical asymptote, it has to be x equal some number. Okay. Yes. All right. So looking here, it says the limit as x goes to the infinity from the left. So the first thing I'm going to do is identify where is my asymptote. So when I look here, where does it appear that my function is approaching? Right here. My asymptote is
-3.
-3. Do we see that?
Yes.
And do I have a horizontal one?
Yeah.
Yeah, we
2.
at 2. Just so that we can all acknowledge. All right, so we see our asymptotes are drawn in. And we have a vertical asymptote at x equal what? -3. And we have a horizontal asymptote at y equals 2. Horizontal is y equals, vertical is x equals. Agree? All right. This says the limit as x approaches a, your asymptote, from the left. So as I'm coming from the left, what is it doing? It's increasing. So it's heading towards positive infinity. Make sense? So for this case, when a equals, what's our a? 3? -3. So when a equals -3, f of x is going towards positive infinity. All right, again, our a still equals -3. So as I'm coming from the right, what is it doing? Towards the asymptote. Now where am I heading? To negative infinity. A plus and minus where? This right here. Oh, because it's telling you you're coming from the left or the right. So if you go back here, this right here, the minus tells you you're coming from the left. The plus tells you you're coming from the right. Got it? All right. Yep. So now we're going to do our horizontal asymptote. Where's our horizontal asymptote? Y equals 2. So normally it's going to be y equals some value. And in this case, it's y equals 2. I forgot to write our x here. Sorry. Okay. So y equals 2. And we're going to describe what is happening here. So 10. So what's going to normally happen is that it would be going to negative infinity or positive infinity. That's if there wasn't a barrier. Does that make sense? However, well, yeah. So when our limit as our function, negative infinity, which means I'm going forever to the left. As I go forever to the left, what am I trying to approach? 2. The limit as x goes to positive infinity, which means I'm going forever to the right. As we go forever to the right, what are we trying to approach? 2. Will we ever approach it? No. Why will not? It's an asymptote. Okay. In algebra 2, we focused on never crossing any type of asymptote. However, there are special case formulas, as you can see right here on the note, that you may cross a horizontal asymptote at a certain point. Okay. And it will have some type of behavior on the sides. But just keep in mind, at this point, as we dive deeper into functions, we may come across a function where it will cross the horizontal asymptote at one point. Okay. All right. Just want to give you that heads up. All right. So how do we feel? What's not great? Oh, okay. Huh? All right. So next, we're going to talk about how do you find the horizontal asymptote. There are 3 rules that we follow for horizontal asymptotes. Okay. So the first rule that we follow, it's all based off of your degrees of your numerator and your denominator. Okay. If the degree of your numerator is greater than the degree of your denominator, then no matter what, your horizontal asymptote is going to be at y equals 0. If the degree of the numerator is less than the degree of your denominator, no matter what, your horizontal asymptote is going to be at y equals 0. So for example, we have y equals x minus 2 over x squared minus 9. The degree of my numerator is 1. The degree of my denominator is 2. In this case, the numerator is less than the denominator. So the horizontal asymptote is at y equals 0. Does that make sense? Okay. All right. It's always like that. As long as the numerator degree is less than your denominator degree, it's going to be y equals 0. Got it? All right. If it's more than 1 degree of separation, that's where you'll possibly have those crossings in the horizontal asymptote. Okay. All right, on to the next one. So our next one we have is if the degree of the numerator equals to the degree of the denominator. So if they're equal to each other, it's now going to be based off of the ratio of the leading coefficients. All right, cool. I don't know what happened. The leading coefficient of your numerator divided by the leading coefficient of your denominator. So I'm just going to write for numerator n over denominator, meaning leading coefficient. And let's write an example. So we have y equals 8x squared minus 1 over 2x squared plus x minus 3. What is the degree of my numerator? 2. What's the degree of my denominator? 2. So they are equal to each other. Does that make sense? When they are equal to each other, all you're going to do is focus on their leading coefficient. So the leading coefficient of the numerator is 8, and the leading coefficient of the denominator is 2. And you're going to write that as a ratio, aka a fraction. So my horizontal asymptote is at y equals 8 over 2, which equals what? Which is 4. And that's where your horizontal asymptote is at. And that's because my degrees are the same, and all I'm doing is using the leading coefficients. All right, our last rule is if the degree of the numerator is greater than the degree of the denominator, you have no horizontal asymptote. Say it with me. No horizontal asymptote. Does anyone remember what you have? You're going to have a slant or oblique asymptote. Oblique, O-B-L-I-Q-U-E. So for example, we have y equals x squared minus 5x plus 4 over x minus 2 or 1. That's fine. It's an example. X minus 1. Okay, I'll fix it. X minus 1. Is that better? All right, so the degree of the numerator is 2. The degree of the denominator is 1. So in this case, n is greater than d. So there is no horizontal asymptote. Got it? And that's just because the degree of the numerator is greater. How we feel? All right. So making sure that you understand, you're going to do example number 2. You're going to look at the 3 problems and say, is there a horizontal asymptote or not? And that's where we're going to stop at. Got it? All right. So you're doing this right now. And you can do it in 3 minutes. I believe in you. And tell me what it is. You got it. It is. All right.
Also, you didn't post the second module for. I looked on the thing and it just said module. It said module 2 for.
Okay, so really quick, on here, again, you're paying attention to the degree of the numerator. So the degree of your numerator here, this is a degree of 0 because there's nothing there. The degree here is going to be 2. So n is less than d, which means that you have a horizontal asymptote at y equals 0. Okay, the degree of your numerator here is 1. The degree of the numerator here is also 1. So this means that n equals d, which means that you're just going to focus on your leading coefficients. So your horizontal asymptote is at y equals 3 over 1, which equals 3. Okay. Lastly, we have our degree of our numerator is 2. The degree of our denominator is 1. So in this case, we have that n is greater than d. And because n is greater than d, there is no horizontal asymptote. All right, good job.